I will introduce Shahi Yener. Okay, he said he is the CEO of Alpha Ruin International. And of course, here we have the president of Alpha Ruin International, Professor F. Wang. But first of all, I will introduce Shahi, yeah, because he said I'm his teacher in physics. But I said in return, he's my teacher in management. Okay, now without further saying, okay, I will give the microphone to you.
Thank you very much.
Okay,
folks, Dr. I've been told I have a loud enough voice, so I'm going to leave the microphone down, or else I might hurt somebody's ears. I just have a brief introduction today, and then I'll come back up and speak with you all a bit more. I think I know most of you. My name is Shahi Yener. You know me as Shah. I'm both Managing Director for the United States portfolio for W.A. Harper, and also CEO of AlphaRate, an apt student of the next person I'd like to introduce. Usually I do a brief introduction, but if you'll bear with me, I'd like to go through a bit of a formal introduction. Today is a special day. And some of the technologies we're going to show you have never been seen by people outside of this group. And so I want to do this the right way. So bear with me for just a moment while I do a bit of a formal introduction. Our next speaker is my good friend, mentor, and professor. His name is Alfred Wong. He is a fellow of the American Physical Society and also a professor of physics and astronomy emeritus at UCLA. In 2016, he left UCLA in his full-time role to start a worldwide company called AlphaRate International Limited, with a focus on developing clean energies to help make the world a better place. Professor Wong's scientific discoveries have been published in over 160 different journals, including 44 different papers in the Physical Review Letters or similar publications. He won't tell you this because he's a very humble man, but he's actually published once a year for 44 years, usually on his birthday. And he is a prolific and a very profound writer. Sorry, Professor, I had to share. His specialization lies in the field of ion dynamics, and both in linear and nonlinear phenomena. What that means for us is how ions, meaning charged particles, get the world to do the things they want to do. Professor Wong is the holder of 20 different patents that have been granted by US and foreign patent offices, and an additional 20 patents pending in the areas of energy, environment, and communications. In 1967, it's a long time ago, makes me feel a little bit older. In 1967, he was awarded as a young man the Alfred P. Sloan Fellowship, a 2-year research grant for promising young faculty members. In 1985, he received the American Physical Society Award for Excellence in Plasma Physics for the first definitive experimental demonstration and fundamental study of self-focusing and the collapse of Langmuir waves. In 2008, he was conferred an honorary degree by the University of Macau for his contributions in plasma and physics and science. He has graduated over 29 PhD students in his 40 years at UCLA, and 1 in his time while he was at Princeton, which was his alma mater. Many of these students have gone on to hold key positions, such as chief scientists in industry, government, and universities. He's directed the research of over 30 postdoctoral students and engineers at UCLA and in the companies that he has started since he left. He's devoted to solving the most challenging problems in environmental physics, the largest of which is how do we solve our current energy crisis, our reliance on fossil fuels, and find something that's a better and cleaner solution. So if you guys will join me in welcoming to the stage my dear friend and mentor, Professor Alfred Wong.
Thank you for a very kind introduction, and also to Professor Lee for opening up this institute to give this personal talk about this what is regarded as the holy grail of physics and engineering, namely fusion. And if I may, let's see, can you turn on the first slide? Yeah. The first slide shows you that the next slide, please. Yeah. The next slide shows you that we are facing in this planet Earth a very important, maybe the global warming. Okay, everyone knows that. Planet Earth. However, our planet, if you look at the whole universe, it looks like a piece of dust. Now, dust electric become very important, as I will tell you later, but our piece of dust is the only planet we have. And we don't have another dust to go to, So the prediction is we have 11 years to fix up this earth to be habitable. So we don't have that much time. So I'd like to share with you what drives the whole universe. Because when we are in trouble, we look at other planets, the stars, and the sun. The whole universe is driven by fusion energy. So fusion is the energy that drives the whole universe. Therefore, you say, why can't we do it? Okay? Because there's nobody up on the sun, on the star, but yet they've been shining for billions of years. And they seem to be doing well without anybody. So we have all sometimes there's a program called SETI, Search for Intelligent Life. And because they said in here. So we have to search for that. But you look at the whole universe is deriving its energy from fusion. So we like to learn about how we can get fusion today. And I hope that that you will share my dream is to have fusion in my lifetime and not in somebody else's lifetime. Because fusion has been regarded as always the fusion of the future, but we want fusion now. So today's talk, I want to share with you our 10 years of progress up to this point, and a lot of things that I'm going to tell you have never been explained or propagated from this room on, as our CEO Shah has pointed out. So I hope to lead you through this presentation to show you how we can get fusion today. Okay? So the next slide, please. The next guy. Okay. I don't have to really go over the urgency of the climate change, given the flood, the fire, and all kinds of ailments that we, in fact, the 16-year-old girl that was telling us that we're not mature enough to worry about the climate change, but to resolve the climate change problem, we must have a new source of clean energy. Okay? So this is urgent. We have about 11 years or so to fix the problem. And 11 years not that long, I suppose you understand. Okay? So the next one. Next slide, please. Yeah. The fusion power is kind of the answer to it, and because it's 1 kilogram of fusion fuel equal to 10 million kilograms of coal. So that is courtesy of Albert Einstein, who said E equal to mc squared. So because of that equation, you have 1 kilogram fusion fuel really take care of the 10 million kilograms. So it's just tremendous. That's why the sun and the stars are all burning, and they don't seem to be running out of fuel. Okay, we do. But so the next one, please. I can advance this. Yes. Okay. So. Okay. So we are. I want to show you this picture at the beginning of the talk, because this is during solar eclipse, you can see the sun's surface. And the sun is our closest fusion reactor, natural fusion reactor. So on the right-hand side is the experimental result that we see, we now have observed in our lab. So we're trying to, you might say, imitate the sun. In fact, this trip from US to here, I brought this demonstration for you, so a live demonstration, you can see it today, that demonstrating this so-called the alpha technology. We call it alpha because it stands for A, but also the product of alpha particles. Now, alpha particle of fusion are very safe, unlike neutrons. So the alpha really is the nucleus of helium. So we know helium is very safe. So alpha particles are the product of fusion, not neutron. Whereas the fission, you get neutron as the product of fission. Okay. Hello? Okay, good. Thank you. So by, you can see there's somewhat similarity between these two, and we can now hope to produce the sun on demand in the lab. Okay? In other words, you cannot have the sun on demand outside, but when you're inside the lab. So we hope to get the sun on demand inside the lab. Okay? And so this, I always want to see that this is a circle. Okay? And I got the idea from on the Chinese dinner table, you have the lazy Susan. Okay? So that is round and circular, and you all have second chances. Okay? So we want to emphasize is the rotation symmetry. So all the galaxies in the universe are always round, because when you have something circular, you don't have beginning or end. You go on forever. Okay, so here you see that we hope I'm going to describe to you the process that we can imitate the sun and in a safe way. Okay? And we're going to give you a demo as well. Okay, so the next one, let me use this in my pocket. Oh, you got it. Okay, so your question is something so good, why does everybody do it? Okay? And the answer is everyone is doing it, except I want to tell you the difference between the conventional research and what we're doing here. Okay? I hope you pay attention to this very important table. And also I put posters all around so that at the end of the talk you can go around and see it too. But the difference between our approach and the conventional approach is this. Conventional approach trying to do this by brute force. Okay? And what we're doing is so-called controlled fusion reaction. The hydrogen bomb is an uncontrolled fusion reaction, and which is not much use to most of us, but we want control fusion. And that's a difficulty to having control. So first of all, can you believe that the only barrier to fusion is called the Coulomb barrier? That means when you're trying to put two positive charges together, they don't like to be together because the like charges repel. So that is why everyone, without exception, trying to go to very high temperature and trying to force these charges to come together. And so we said this is a good force way, And you know the Chinese way is always natural. Right? So since we have negative charges, we know that unlike charges attract. So I decided 10 years or so ago to really get into the business of overcoming the two of them, okay? By introducing not just positive charges, I introduce a lot of negative charges so that we neutralize that repulsive force. So the difference between us, outer ring on the right, conventional that one you put forth, you put a lot of electrons in that vicinity, okay? So, and then because they use a very high energy, they cannot have very high density at the same time. Just like you're trying to force a lot of positive charges, you can't force a lot of them. So, however, in our case, we emphasize a lot of positive charges, negative charges at low temperature. And so that's why I could do it in this small device that you see. Okay? Just next to you. And you don't, no fear. This is control. So we want to point out that difference, that they use a very high temperature, 200 degrees to start. Here we're only using something, 1,000 degrees or 2,000 degrees. So it's a tremendous difference between the two. And so the input energy often in megawatts, and in our case, our energy, you're going to see two demonstrations today. They all run around. In the second demonstration, we only did a 1 watt to see fusion. So over there, in all conventional fusion, you need megawatt to even see fusion. So I hope to give you two demonstrations. One is you see the water and steam on the first one, and the second one, we have to show you the fusion particle and be in a very billions of degree coming out of what we're going in, becoming a few hundred degree, 3,000. So there's the idea that we can do the fundamental differences between our approach and the conventional approach. Because the conventional approach has been there for 70 years, and they still say fusion was still 20 years away. So it's always 20 years away from today. So we like to say we want to do it now, okay? And you understand, I hope at the end of this talk, you understand why we think we can do it now, okay? So, and of course, if you do put forth millions of dollars, in our case, the one that you can receive thousands of dollars to make. Okay? And most important, at the end of the talk, we now discover that you can even do it on a piece of dust. That means you can do called micro nano fusion and nanoscale. So those of you who admire the robots, and sooner or later everybody will have a robot at home to cook the meals and to sweep the floor and everything. But the robot does need energy too. So we can have fusion energy, all the circuits are autonomous, and so the robot have a life of its own. Okay? And by scaling too. But anyway, so we want to show you today, because of the fundamental difference between us, that if we want to lower the barrier to make it feel other than trying to force it, that's the difference between the two. Okay? The next slide, please. So this is so-called that we have a major barrier of fusion, only one barrier. So if we can lower it, we can do a lot. So also we now say that if two charged particles, repel each other, why not make them neutral? Okay? So let's do neutral fusion. And of course, the neutral, it means that the positive ion and negative ion come together, and they don't have such a repulsive force. Okay? So, and I advise some of you, you go home, take two magnets, put the North Pole, you push it will not come together. If you put a North Pole and a South Pole together, it will come together very quickly. Okay? So you can try that little experiment. So anyway, we also, by using neutral fusion, we can actually view up the density that is possible. Because when you want to do fusion, you take billions of reaction to have more power out than in. So not only fusion is difficult to do, we actually want more energy coming out than we put in, otherwise we don't want to do it. Okay, so next one please. Okay, I'm going to introduce some of the invention that would led to the present situation. And also I want to tell you that at some point in my talk, once this device warm up, we will actually show you the fusion process that gives you more energy out than you put in. In our case, about 30 to 40% more energy out than we see today. And then later on, I show you another demonstration that actually gives you 100 times. Okay, so those are the two things to prepare for this talk here. Hold on a second. David, when you're ready, okay? Yeah. So they're warming up this call so that we want you to see on the screen. So outer ring, we have a number of inventions. I already covered two of them. Is lowering the barrier by electrons using neutral fusion. And then we found out something very interesting. Ion neutral coupling. We can actually make a positive ion move a lot of neutral. We found out one positive ion can move 500,000 neutral. So we use the ion to push the neutral, and the neutral don't repel each other. The gentleman that just set up this, basically the monitoring, you will see it. We show you that the current that we pass through the system, and also we show you how the energy going in, and then the energy coming out. And that's called a gain. If you put energy coming out over the energy going in, you get a gain. Equal to 1 means that you get as much energy as you put in. And when you have 1.4, you get 40%. Okay? So this is a simple experiment can give you 30% to 40% more. So we want you to see that. Okay? Okay. I keep talking until you guys are okay? All right. So. Okay. I have prepared an animation for you so that you see our technology is to rotate the gas or the liquid, but mostly the gas. And you can see as you're rotating the gas, you develop very high centrifugal force. Okay? Now our thing is different. Go to the next one. Yeah. The next one. Now that's a Coulomb barrier. I already mentioned this repulsive barrier that we can lower it by The next one, please come. The next one is just, I have altered the poster on the wall too, but basically over 10 years. Huh? 1.26. Okay, the green is the, huh? Is the game. The blue, the blue, the red one. Yeah, that is, okay. And then here, this one. Oh, it is one here. But this is the game, right?
跟客人是怎么做这个数这样做，也有一些参数是做这个，所以即时没办法即时算，即时算出来也是。
All right, we were just informing me that right now we have a gain of 1.3. This number represents the gain. That is, we put in current and voltage, we get the power input. And then they look at the temperature of the water, it get heated up, and the steam coming out, and you get the number 1.32, 1.25, and so on. I just want to show you as the thing warming up, you get up to 1.4 gains. Okay, so we during the recess time here, you're welcome to walk around and see the thing. But right now, I just want you to know that the warming up, you can actually monitor the gate. The current put in, the voltage you put in versus the water and steam. Okay, we actually have a video to show you can use the steam to drive a turbine that will drive the electricity as well. Okay, but anyway, let me continue with this 10-year progression, because that is important, because all of you would, especially my friend, our board member, Dr. Costa, he always asks me for partners. Okay, focus and get something out. Okay, so the 10-year progress, to show you back in 2009, we were already thinking about making a chip that makes called the alphabet. Okay? At that time, we're using a radioactive decay source, but now we can use fusion alpha particle fusion. So back in 2009, we were already thinking about making a small power source chip. And then in 2010, we start looking at the proton ball reaction that will give you helium at the output. And then in 2014, we further proved that we can get up to a pulse megawatt level. And so up there, 2014, we also see the first, we call it viewing sun. We start making something that looks like the sun in the lab. So, and I would invite you when you, after this talk, to look at that poster over there on the wall. They trace our development of our intellectual property from 2009 to the present, and our chairman CEO will talk about that later after my talk here. But we just want to go through this timeline for you so that you can see the progress from looking at water, hot water, and steam to looking at real fusion energy in terms of particles. Those particles come out with millions of electron volts, like the photon, helium-3, tritium, and so on. They all come out with much higher energy than within. So back in 2016, the 2017, 2018, you're going to see a demo today on the fusion particle coming out that make the cloud chamber check track the content you see. So we now progress in computer. This year, we now found that the dust particle can have fusion on it, and therefore we call it a fusion star. Okay, so we go through this whole 10-year progression. Okay. Now, before we show you let's show them the video, because people always like to see something moving. Times a new picture. But by seeing this animation, you better appreciate what we have here. So this is a operating system. Yeah. And so I want to explain to you, we use this is a unit that you can see. It uses an electromagnetic field to drive the gas around. So we don't use a mechanical motor, but we use an electromagnetic electric field to drive the fluid, which in this case is the gas. You see that is what making the fusion process. Okay. Now we drive the primary neutrals. We do have ions in it, but the ion each ion can drive 500,000 neutrons. So ions are the minority. Okay. So if you keep going, as you know, as you go faster and faster, just like on the amusement ground, you feel you're being pressed against the wall, right? And this thing actually can go up to, our record is 700,000 revolutions per second. Okay? Now we know it's sort of make you dizzy. So this thing drive hard, and you can just stop that. Can you stop this for a minute? I need pointer too. There's a pointer, okay? This one? Yeah. So go back to that here, right here. So by having the thing rotate very fast, it's pressing against the wall, and then you have the fusion between the fluid and the wall, okay? The gas and the wall with the electron between them, okay? So our invention is the gas moving very fast and against the wall. That's what happened. So when you see that display, we actually have gas moving very fast, okay? Now, the next one, I'll keep going with that fusion and see the fusion. So this is the unit we bought from Monterey and Gardena to here, and we got it working for you to see. Okay, so we're ready. You can go and see the picture on the screen. Just happen to the rotation speed and so on. Now we want to show you another video so that you got into your head what we're trying to do. Now here is a bigger chamber. Here is the source. And this bigger chamber, the source is located this side. And we will see, because of rotation and because the fusion occurs on the dust themselves, you will see on the wall the scratches on this interchamber. Okay? And as they rotate, they also come out of the chamber and they actually make we call helical orbits. So you see that the same rotation before, except you now have the dust coming out, or the chalk particulate coming out, and they just speed up a little bit so that you can see the cycle. You get fusion going on, and then they start coming out of this region towards you, and you should see the side view of the kilowatt to megawatt output. Now here, you see that, can you stop it for a minute? Not only they make scratches in the wall, they actually start coming out in this helical orbit. And they are actually carry the fusion on those little units, and we call it fusion star. Okay, if you go to that, you'll see the you go to that. See all this dust of the chart, particularly actually inside the field, it makes this circular orbit. Okay, see this, they're kind of like the fireflies in Taiwan. They have this, because they have fusion with them, when they hit the wall, they actually make marks on the wall. And you'll see some of the record, there's so much energy of those fine charged particles, they actually scratch the wall with carve up the tracks. Okay, so, and I would invite you to see some of that on the picture on the wall. Okay, but keep going. Okay, so basically we have, let me sum it up to what we have seen so far. We have the basic idea is rotation. Okay, to make something rotate, and we invented a special way to rotate something without mechanical rotor. That's important, because no mechanical rotor can go at a million frames per second. No material can withstand it. So anyway, we have this special invention of rotating either the gas or the liquid against the wall. So when you have fusion reaction between the rotating fluid and the wall, you get the fusion, the power coming out. Okay? So are they ready now? Can you? Yeah. So right now we're going to show you the data actually from all the bulk and monitoring the temperature of the water, the temperature of the steel, and the power coming in. And then we take the ratio between the water and the steel, and this one and this one. That is, I still want to speak that let's take a second. We prefer the second one now? Okay, so I can go to the second one. But the first one is missing. Okay, all right. They actually, I think it's the first one by showing all the curve going out to show you. And the first one they get a gain of 1.35. But here, we show you the second one. And the reason I want you to the second one is before that we call it peak target injection. Okay? Now, fusion is so efficient, so desirable, because you can put particles that go in about 2,000 degrees and you get millions of degrees coming out. And they call MeV, and MeV stands for millions of electron volts. Okay? So you can get something like thermal energy, you get millions of 100 times and so what we're trying to show you here is this picture of we have a beam coming down here, hit the target here, and then the infusion product come out and catch by the counting, okay? Now, yeah. Okay. Now, I have actually carried this source. This is the deep source, okay? It's quite compact, see? And so this beam generated power about 1 watt to 5 watts, okay? And the target is here, okay? So we can actually shut off that projection. Okay. All right. So, and I'm using a laser to show the beam for those of you in this world you can see it. You see that the laser beam represents the beam, okay? We cannot link a neutron source to a high source on the airplane. And so this one represents the beam coming down here as source, and then it hit the target here, and the target generates this energetic particle you see on it. This is called the cloud chamber. Now, this is actually running in real time, right? In real time in Los Angeles. Okay, we cannot bring the whole unit here because of the trouble limitation. But if this thing rotates so that the coating does not contain too much material, you will see much less track. But when you rotate this thing to one with the higher coating, you actually see much higher fusion output. Okay? So we just want to use this demonstration to show you that we can use something like 1 watt of beam power to generate billions of degrees in temperature product. And this is a kind of invention at our lab. Now we can do this kind of small scale experiment using a few watts, and we can then do experiments very quickly. We can actually change the target within minutes. Okay? Now we can design target of different coating, different sizes, say from lithium to CD4 and so on. So we can change the target very quickly, and also we can put a lot of electron here too, so that we can test the idea how the electron lowers the barrier. Okay, so by this is cloud chamber is a very good way to look at fusion particles. So that's why we make use of this. And so they are actually doing experiments right now online, so that we can see when this thing rotates, we can at the right coating, and you get much higher fusion output. So this is a way to show you not only you can look at water and steam, you can look at energetic charged particle, which can go directly into electricity without going through the steam cycle. So that's why fusion is so attractive, that you can you don't have to go through the Carnot cycle, which usually only 40% efficient. By doing direct energy conversion, you get efficiency over 90%. So we go directly from fusion products into electricity. So the people in doing experiment right now, and over in, we just want to show you online, if you could want this thing here, but instead, I bought this mock-up model here using the laser beam to show you. So for those of you who are this side, you see the laser beam is a way to represent the beam. And by rotating the target, I can make different angles of the target with respect to the beam. So we can look for efficient way of designing this according to micro, mini, fusion reaction. Now, at this point in time, I'd like to tell you why we want to go into the small scale and why density system actually works better. Now, you see today, all the fusion devices are very, okay. I can get that. Can you change the slide? Okay. Oh, yeah. So this is the last picture of showing that the source, we call the source, is the source that we have out here that you will see after we conclude this talk. You can see that the source in the center can actually produce a lot of charged particles coming out because of the magnetic field. So those are what we call a charged particulate or dust. And on those dust, you actually have fusion going on, exactly like the star in the sky shining on its own. Okay? So we hope to do fusion stars, and so those stars are produced by the units on the left, coming out to the right, and we can generate energy as they go out. So you can fill up the whole chamber with those charged dust. Okay? And therefore you can go into what we call 10 to kilowatt to even to megawatt level. Okay, so the next next slide, just want to show you in our lab we also are studying we call flying dust. You know, a dust is when you fly and the fusion on it, it is a free agent length because there's no, just like the star in the sky, there's no power going in. It is self-sustaining. So we want to point out to you today, we can now have discovered the self-sustaining reaction on charged dust. And because of that, you can see on the right, inside the little circle, are actually a group of charged particles together, and they being levitated, so they're completely away from the wall. So you can see that if they produce fusion on their own, that means the gain is infinite. Even though we don't have to put energy in, they actually self-burning. Okay? And kind of like those of you who do the campfire, you see the embers flying out. And those are the embers of fusion process that are free flying objects. And so I want to tell you why we do all this, because we want to show fusion in our lifetime. Okay? So we're trying to not using a big machine, trying to do small scale, with tabletop such as this, and then to do even a larger system. But it's much cheaper, as you all know, to make small objects and then make big changes. Instead of having to wait for a whole year doing it and find out that doesn't work. So we're trying to we have this type of experiment in the lab. As you go, at the end of the talk, you can see all the many paper compounds that we make so that we can try out different ideas quickly, okay? And inexpensive too, okay? Now, I'm almost done. Let's go to the next slide, please. The next slide will show you that we have a three-phase, three-pronged approach. We do theory, we do computer modeling, and we do experiments. Okay? Because computers today are so powerful, they can actually test a lot of our ideas. We don't need to see what they're going to actually do that. And I'm sure that my friend Shah will tell you more about this side, but let's go to the next one. The next one is patents, okay? We start finding patents in all the countries represented by that. The next one is. And then we have grant patent, and then we also have third additional patent in the world, okay? So, next one. And so the whole idea is that we think we can generate more efficient fusion power at every scale, from small scale, and then on the right-hand side, circuit board, to home use, to car, and to home community, okay? And in fact, those of you who read the paper that PG&E is cutting back, have scheduled back out of the different communities in California. So we have different scales, okay? And next one, please. And so this just tells you that we can now do so-called integrated experiment by trying again this idea using platforms such as this, okay? Next one. And so we want to show you that renewable, we're nuclear fission, because nuclear fission was so dangerous after the Japanese accident, many countries have banned it. So we want fusion, nuclear fusion, just like cricket. So because it's clean, the next one, it's safe, it's capable of different scale operation, and then next one, geographical, independent, and you don't even have to depend on the grid, and so it's no disposable problem. So anyway, most important, you can do all scale. Okay, next one. So we already see the demonstration on the rotation dynamic. You've seen it in the computer, and now we want to show you that we can get a larger system through the use of the fine dust. Okay, and next one. And so you will see the trap on the wall. We got a picture of the trap that we call it, often we say something cast in stone with the beautiful, so we cast in stainless steel. Okay? So you can see the trap by the fusion particle casting their energy and mass on stainless steel. Next one. So you already see the demonstration. So one of our investors always interested in getting rid of this one, and so we deliberately want to show you today this unit that can get 1.3 to 1.4 gain. Okay, and so but most interesting, I want to point out that in that machine we actually have a commercial third party called the Evans Analytic Group that analyze materials. And they're the third party that have actually analyzed the dust that we have generated that have caused fusion. And then in the next two slides, you can see we build one unused new lab 6 target, the one below is the used one. And the next slide show you the one in the used one contains 4 times the helium content. Okay. independent company that analyze the dust that we have produced. Okay? So just wanted to show you that because of the DET lab, so we're trying to make sure we have third-party validation. Next one. So the one that you just saw here, the in-target system, is actually one of our inventions to be able to do fusion rapidly, because we really don't have that much time to lose. We only have 11 years. So we want to show you we can do experiments 1 to 5 watts, and we can get clear fusion product. That's one of our product invention. Okay, they enable us to be fast ahead. So next one. This is we've already seen this. Yeah, this is the one you saw before. When they rotate the right way, and by the way, you can change the car composition material and try to optimize the amount of fusion output. Okay? Remember, those are fast particles, MeV, energy, in terms of energy per units of degrees. Okay, so next one. Now that's the end, and let me turn over now to our business experts and our CEO of the company, Sean. Why don't you come up and tell us what you think is the future of
Please round of applause for Professor Walker. So guys, I hope what we've shown you today is that we've got some experiments taking place now for you that are yielding results that we've not seen in any environment before, academic, nation state, and certainly not in private practice. I'm here now in a dual role, one as a venture capitalist and one as the CEO of an energy-based company. And so I'm going to try and give you a little bit of perspective from the business side, and if I can, as the hopefully the last graduating PhD students in Professor Wong's class and Professor Liu's class, a layman's interpretation of what's really going on within these devices. First, why do you care? It's fusion, right? You hear a lot about fusion. We've been talking about it for literally nearly a century. 70 years in practice at least. And so why do we care? We care because fusion is a solution to a problem that troubles us all. Energy creation. And I want to bring it back to a very basic analogy. Energy is the world's largest market. At last count, some $64 trillion market. It affects every person in this room and every device you have, from your cell phone to your automobile to your home. It touches every single person's life. And so therefore, the ramifications are large, not just in terms of economics, but in terms of conflict, in terms of humanity, in terms of culture. So we're dealing with a large and working market. Fusion in particular has been called the holy grail of energy creation. Why? We have solar, we have geothermal, we have hydroelectric, we have fossil fuels, depending on who you ask. Any one of these is a viable solution. Fusion is the only one that has what we call energy gain, or unity. And how many here have heard of the most famous physics equation in humankind, E equals mc squared? Anybody? Show of hands, please. I know you've heard of it, Professor. All right. So, and you guys heard the second one, F equals ma, which is the second most famous. The most famous, E equals mc squared. Take a minute to think about it. Energy equals mass times the speed of light squared. Professor, how fast is the speed of light squared? I know you know this one. Come on. Thank you, sir. Yes, thank you. So it's an enormously large number, which means when we talk about fusion, we're taking two particles, jamming them together. And when they do that, they become one. But a very, very small part of what used to be one of those particles is lost. It's called a mass defect. That mass defect is actually converted to energy. That means mass, which is the m in E equals mc squared, has been converted to energy. If you flip that equation around, E equals mc squared, what we get is that mass being converted to energy times that enormous number that Professor Gano just shared with us. That's an enormous amount of energy. It means that if you want to power the state of California for a day, you could do it on about that much fusible material. Think about that. relative to the trillions of tons of coal that would be necessary to do the same thing. Second, as I was saying, it's the only thing that allows us to have more energy out than in. There's no more efficient system, right? We always argue about efficiency in energy. How much am I losing, right? To exothermics, to phase transitions. Fusion is the only thing in the world that gives us the ability to actually have more energy created than not. When Professor Wong is referring to a gain of 1.4, what that means is that for every kilowatt that's going into the system right behind you, 1.4 kilowatts of energy is being created. Because matter is being converted to energy and it's making up that 40% accretion that we're talking about. That's why it's so valuable. Now, we've heard a lot about nuclear power for a while, right? And we typically associate that with Chernobyl and Fukushima right away, right? Those are fission. That's where we take an atom and we split it, usually very heavy particles, we split them. And that little piece of matter is converted to energy. Well, it's very dangerous. It can have a chain reaction. It can run away. And it just so happens that it is not having energy gain and positivity. And not only in addition to being very radioactive, there's no possible way for that reaction to be stopped once it hits a chain reaction, right? So we have this dangerous radioactive mechanism that's quite hazardous to handle, and lots of people are ramping it down. It also happens to be about 1/7 as efficient as fusion. So this is why fusion matters. It solves a myriad of problems. It is the only thing that can actually give us energy positive creation and distribution. And if we can solve it in our lifetime, hopefully in the next 11 years, we won't all blow up in a fiery ball of flame. So if you look at fusion from a venture capitalist perspective, it's a really unique time to be investing, right? We see the privatization of space programs. We see things that have previously been done by universities and by nation states being private for the first time. Fusion is just hitting that curve in the terms of investment capital. And you would think that technically it's a very challenging thing to look at. You've known me for 15 years, CT. Have you ever seen me invest in anything nearly this crazy? No.
All the time.
Thank you. Remind me to rehearse answers with you before next time. On a serious note, this is a big investment for us, and it's the largest investment in W.I. Harper's history. So why make it? Well, because we have the ability to affect change and to affect it now. It turns out that assessing fusion is remarkably easy. One, can you do it? Is fusion present? And it turns out that, yes, in fact, Professor Wong can do fusion. And not only can he do it, we can do it at powers that have never before been achieved. The competing technologies, Commonwealth, Tri-Alpha, General Fusion, Helium Energy, backed by your billionaire du jour, all start at 50 megawatts as their initial input power. That means to be successful, they have to have at least 51 megawatts coming out of the system. The only option available to them is to build large base load stations that essentially recreate the energy grid that we have today. Professor Wong can do fusion at 800 milliwatts. That's 1/100th of what powers the normal light bulb. So yes, we can do fusion, we can do it in a novel way. Two, is it safe? Am I going to create radioactivity? Am I going to have neutrons? Am I going to kill people? Is it able to be weaponized? Yes, it's safe, and no, it can't be weaponized. What we're talking about is proton-boron fusion. It happens to be what we call a neutron. It means less than 1/10% of every reaction yields a neutron. For those of you who don't know, a neutron is the neutral particle at the center of an atom that has no charge, therefore it can travel with everything, including you and me, which is not good. Unless you're doing cancer therapy, which is very good, if you can target it very closely. So, we have fusion, and it's safe. Now, PB11, proton-boron fusion, happens to be very challenging. The propensity for this fusion to take place is hundreds of times more challenging than what other fusion companies are taking on, because they're just hoping to get fusion to work. All of the other people you hear in this space talking about their environments ready to do fusion have not actually conducted fusion. It means they've reached the hundreds of millions of degrees capable for their type of fusion reaction to take place. We've done fusion, and it's safe. So now the big question, is there unity? Is there gain? As Professor Wong just showed you in our steam-based system, in fact there is gain. 40% gain, and potentially up to hundreds of times of gain. And that's the secret, right? Because the last thing you have to ask yourself about fusion is it viable? Is it commercially scalable? Can we actually use this? Which means, can I get energy out of this thing that's doing fusion and make it move? And let me tell you kind of where that goes. Short answer, by the way, is yes, we can. And there are two ways to do it. If we're looking at this, you have to kind of take a step back and look at the overall landscape. You've heard a lot of talk today about charged particulates, dust, right? Why do we talk about dust and why does it matter? Dust is to physics, to nuclear fusion, as a mesenchymal stem cell, or a stem cell, is to human anatomy. It is the atomic unit. It's the key thing that dictates how fusion takes place. If you can do dust and get charged particulates to have fusion, if you can make fusion happen at that scale, you can control fusion at any level. From a cell phone like this, it would never have to be chugged into a battery source, to a massive gigawatt reactor that can power an entire state. So that's why charged particulates matter. It's a scalability. I should take some notes. Let me make sure I get all these. Second is size, right? Size matters, and bigger is not better. Small is spectacular. And why? Because when we talk about small systems, by the way, if you've ever seen a competing privatized company, it costs them more than our entire Series A round to build the ion source to power one of their room-sized devices. That's just the source. That doesn't include the device, the rent, and the people that run the darn thing, right? Based on what we've run our entire company on for now 4 years. The reason small is relevant is there's an inverse relationship between fields and size. Meaning as things get smaller in the atomic scale, the fields that affect them get much more powerful and larger. Which means now, not only can we run at very low energies and very low powers, but we can have very, very substantial effects on very small systems, right? So this is critical for us. If you're trying to lower the Coulomb barrier, you remember Professor Williams talking about your magnets. You take two North Pole magnets and you try and push them together, they repel very, very heavily. The closer you get together, the harder they repel. But if I surround one of those magnets with South Pole magnets, suddenly the field allows you to get those magnets closer together. And guess what? If you get them close enough, they realize they actually like each other and they fuse. It's called the nuclear well. And that's exactly what happens in nuclear fusion. So you can change the Coulomb barrier as well as other fields and have what you want to have happen take place in small scale. And once we do it at small scale, scaling up is quite easy. Turns out scaling down is not so easy. Scalability is essential, right? As I was saying, the goal of all fusion-based systems is to have something that has more energy going out than coming in, right? In order to do that, we have to have an efficient system. And if we start with a 50 megawatt reactor, which is what is typically table stakes for a tokamak reactor or people that are in this space. Professor Liu, how many tokamak reactors have you seen? Probably 3 or 4 in your lifetime.
Right.
Let's say the East Tokamak, what's the entry power for the East Tokamak in terms of megawatts? At least 50. Yeah. So we're talking 50 megawatts have to come out of the system for it to even begin to be efficient. We are in the case, and this is where the business value really comes in, because we're talking about scale. We're talking about the ability to do to the electric and computing grid, or sorry, to do to the energy grid what computers and cell phones did to the computing grid, right? If you remember 70, now let's say we go back, let's go back 30 years. 30 years ago, we talked about computers. Computers were a big thing that sat in a room like this, and they started getting smaller and smaller and smaller. Until eventually, it turned out that they started getting distributed. The internet was born out of ARPANET, right? This is probably too much of a computer history lesson, so I'll fast forward it. What this happened, what this turned into, was today's internet, and what we know as edge computing. So computing power was pushed to the edge of the computer, so that today, literally, I have 100 times more computing power in this device than I did in college to run a 500-person company. Now, as a result of that, what used to be a supercomputer can now be held in your hand. And in fact, when we look at supercomputers today, they're not just a giant processor. They're actually a box with thousands, if not tens of thousands, of very small processors. Those very small processors look just like the charged particulates or the dust that Professor Wong was describing. And therefore, if I can control fusion at that particulate level, at that minor level, I can get very large reactions and very large output by putting them all together. What that means for us is, while everybody in the world is trying to recreate the energy grid as it sits today, here's a dirty secret of nuclear fusion. Every device that's being built is to generate heat. That heat is going to heat something up, most likely water. That water is going to turn to steam. That steam is going to spin a turbine, and that turbine is going to spin around some brushes that create electricity. And that electricity is going to be sent down some wires, eventually to something that you own. All of that loses energy. It's called the Carnot cycle. If we're lucky, 30% of the energy created in that device at the center of that system will actually reach you. That means 70% is lost through every phase transition. When I convert from heat to liquid, liquid to steam, steam to energy, electricity, I lose energy every single time that happens. However, if I can do two things, which no other company in the world can do. One, if I can push that energy production to the edge, rather than having a 50 megawatt reactor somewhere in the middle of the state of California, if I could put something that looks like that silver box over to your left, that generates 1 kilowatt, which is sufficient to run any house in the United States and everybody's house, I no longer need the grid. In fact, the grid now becomes reversed. We contribute to the grid as opposed to take energy away from it. And two, all of those things are now energy efficient and very scalable. I no longer need a centralized system. So while I wish all of our competitors luck, because as you'll see in my next point, they're all going to have to talk to us to be able to make their systems work, we hope they actually do work, because by the time they actually come to market, they're already obsolete. We beat them to market because who needs a 50 megawatt reactor when I don't have a cell phone that needs to be plugged in, right? It no longer needs electricity. It is its own power device. So, last two things I want to talk about from a venture capital perspective. Intellectual property. IP is critical for what we do, right? We are not the builder of nuclear reactors. That is not the model of this company. For us, a product means that we build a piece of intellectual property, something that generally comes out of Professor Wong's mind, right? If you look at over to your left, here are 40 different pieces of intellectual property that will become products. That IP is built into a theory. It's first a hypothesis, we test it, we arithmetically verify it, and then we put it through a computer simulation. That simulation, you saw some of these appear, is a mathematical simulation as well as a physical simulation. If that simulation matches the results expected by the theory, we then build a prototype that looks like this with the thing behind you. This prototype is an experiment. It is not a product. Its goal is to give you physical results that match the theory in the computer model. If that's done, we've proven that we actually have something in the real world that yields the results that we expected it to do. At that point, we file a patent, or we create something called a trade secret, which is the stuff that we keep to us that nobody else gets to use. The patents are made public. And once the patent is filed, we then write something that can be peer-reviewed. And that peer-reviewed means we have other people around the world look at us. Because the fifth thing to think about as a venture capitalist is, if I can do fusion and it's safe, and I can actually make it positive in energy, and I can extract that energy, am I crazy? The only way to find out if you're crazy is to ask really smart third-party people to come in and double-check the results, like the Minister of Science and Technology, like the father of the Taiwanese space program, like Professor Kostoyanov that ran the nuclear physics program at the University of Sofia, and all the other people that have come through this program. Go out and get third-party results. Put your results out there and let people challenge you, and then defend your results vigorously. And ideally, you win. If you can do those things, we then have a system where ideally, we're not only solving the world's energy crisis, we're making a hell of a return, pardon my language, Professor, on an investment that was very early in terms of early stage investments. And probably the single, and I say this as the provider of the second largest return in the last 25 years for W.I. Harper, we provide the largest return in fund history. And that's the goal and the business aspect of what we want to do. Now, make no mistake, beta on this investment is high. We're dealing with a problem that is the single largest problem tackled by humankind. However, I think we have not only 40 plus patents in process that dictate that we know what we're doing, but that we have a great shot on goal with the resources, the technology, and the results we've yielded so far with third-party validation to show we're not only on track, but we actually have the viability to bring this to market, not only in our lifetimes, but in the very near future. And that's by bringing the IP to providers and companies that can actually build the products from cell phones to nuclear reactors that make Professor Wong's vision from some 40 plus years of nuclear research a reality. So I'm going to stop there and invite up to say thank you and goodbye to the person who's probably been the single most prolific validator of our technology, Professor Lu Li Chen. Look, thank you.
I was assigned to make a break up of this session because after that we'll see the demonstration. Okay. First one is that I agree with Professor Everett saying the holy grail of the energy and also global warming problem solving is the controlled nuclear fusion. The second point I want to bring up is that my physics student, I think he can become an excellent physics professor from what he just said earlier. Okay. Number 3 is about effort. I met him, I knew him in early 1980s. And when I talked to him, he's been solving the new problem. The fact that he published 44 papers in physical review data means he should have at least 44 new ideas, because physical review data only publish paper with important new idea. Okay? And because of that, he has many outstanding results, many fruits results. That's why he received the American Physics Society the excellent performance in plasma physics award. Okay, that's very important. Now, number 3 is that I show you this one. This is we are doing this rotating green. We have the Leipzig there. You can see here, in between, you can see this is metal. You got a track. So that's hit by MEV particulate. Yeah, okay. And you cannot see this one clear. You can see this photo. We just took photo from this one. You can see this one. This is a big one. So you are able to see the track here, this one. So this one is this one. The track enhanced one is this one. Okay? And we have used this one, many of this one actually, to do the parameter search to understand the physics for this project. And we pause here, when you come in, you will see we are able to get a gain from 1.3 to 1.7. Actually, we are able to get not almost 2, but it's 2 or 3, but not too stable. This 1.7, 1.5 are stable one. You can see that both is very stable. Okay, and we are trying to get a better design. Our goal, and I have confidence, is to get at least 3 or above. Because you just said there is no limit of efficiency problem once it's operated. So we carry every experiment, we take the data. So it's there, we can analyze all the physics and get a new design. Okay, number 5 is this machine. What you see here, and then Edward just mentioned, is that they produce fusion from deuterium, they can produce tritium, they can produce helium-3, they can produce neutron, and which one else? Proton also, right? So this is, but now you are not able to measure in situ inside the energy spectrum of these particles. You just spread the particle, get the particle out to cloud chamber, surely the indeed, get a cloud condensation. So it's there, high energy particle is there, right? And then you can see the quantitative, large one or small one. And then you also measure the neutron from outside. But now, ARI ever asked me to use space technology to put a mini energetic particle spectrometer inside. So we are able to measure how many particles, tritium, how many proton, how many helium-3, and their energy. So we finish our design. I think you review and find it's good. So we have put all the detectors inside the chamber. Just we put a satellite in the space to measure them. Okay, and then we have the next Bluetooth communication to our, so we can read the data. So this is, we are doing now. And also we try to effort improve the design to get 3 and above. Okay, thank you very much for coming here.
So folks, I want to invite those of you, I know you're on a tight schedule today. If you have questions, you're welcome to stay around for a minute or two to have a look at the actual reactor that was running the demo you saw today. Professor Wong and I will stand by to answer questions. If they're deeply physical, he'll answer them. If they're not, I will. But us, you're welcome to follow Charles out to the bus.